Functions. A relationship or expression between specific inputs and their corresponding outputs, or in plain English, a bunch of dots that follow a predictable pattern. Functions are cool in that you can only have one possible output, the y value, for every input, the x value. Like, if you're to make a pancake, your input would be the flour and eggs, while your output would be a delicious pancake and diabetes. Except, you can only have one output, which means you only get the delicious pancake with no diabetes. You go, skinny queen. There are 8 basic functions you need to know. Linear functions, quadratic functions, rational functions, radical functions, exponential functions, logarithmic functions, absolute value functions, and piecewise functions. There is a 9th function type, which is all the polynomial functions that don't fit neatly within the basic linear quadratic function category. Those are your cubic, quartic, quintic, sextic, septic, octic, and on and on and on and on. And now you see why mathematicians just lump all of these special functions into one separate, big, large, super, totally specific category, the polynomial functions. We'll get into the specifics of each type of function later. But first, let's talk about the specific behaviors a function can have. These are asymptotes. The formal definition of an asymptote is a line that continually approaches a given curve but does not meet it at a finite distance. This just means a curve will continue approaching a certain value like y equals 0 without ever touching it until it reaches infinity. In the real world, you can think of it as an unattainable crush that you'll never get. I'm not speaking from experience or anything. Anyway, on the bright side, there are a few different types of asymptotes: vertical, horizontal, and oblique. Vertical asymptotes happen when a certain input can't be inputted because the input doesn't give a real output. You follow? Basically, it's when you're given a function like this, your x can't be -3 because then it'll be a function over 0, which is considered undefined. Now, if you're a nerd, you're probably wondering what happens when we get 0 over 0 when we plug in an x value. Well, my dear pupil, this happens. But you don't have to worry about that until you get into calculus, which would be so fun. Basically, for now, your only headache will be to determine which x can occur for your function to be defined. The other types of asymptotes are horizontal asymptotes and oblique asymptotes. And within horizontal asymptotes, there are 2 more types of asymptotes. But we'll get into that later. There are 3 rules to find out which rational function will give you which type of asymptote. First, when the function in the numerator has a degree 1 value more than the bottom function, this will give you an oblique asymptote. That's basically when there's a slanted line where the function will never reach. Second, when the bottom function is 1 or more degrees more than the top function, this will give you a horizontal 0 asymptote. I like to call these bottom heavy because they're bottom heavy. You know? Anyway, and thirdly, if both top and bottom functions are of the same degree, there will be a horizontal asymptote at the ratio between the 2 leading coefficients. Oh, I should probably define what a degree and coefficient are. Essentially, a degree is the highest power of a function, like this, and a coefficient is the number that multiplies each term in the function. Then, of course, it would follow that the leading coefficient is the number that multiplies the term with the highest degree. I suddenly understand why everyone falls asleep in math class. Of course, you also have other behaviors of a function, like an increasing or decreasing function, and a maximum or a minimum of a function. But these are pretty basic. Even your 3.5-month-old puppy could see that. However, something your 3.5-month-old puppy probably couldn't understand is the symmetry of a function. The symmetry of a function is determined by whether a function is odd or even. Remember that whole degree of a function talk from before? Yeah, well, it turns out that isn't just a medieval torture method designed to make you bored out of your mind. If the degree of a function is odd, or in other words, if the exponent of the leading term is odd and any other consecutive terms is odd, the function will be symmetrical around the origin. This just means that if the function is turned around 180 degrees or flipped upside down, it will look the exact same. Kind of like how if you rotate a minus sign 180 degrees, the minus sign will still look like a minus sign. Now, my bright pupil, if the degree of the function must be odd for the function to be classified as an odd function, how do you think the function should look for it to be classified as an even function? If you said degree must be even, then you sure are a smart cookie. If you said anything else, well, your spirit animal might just be your 3.5-month-old puppy. Symmetry for an even function must be across the y-axis. This means the right side of the y-axis must be the mirror image of the left side, and vice versa. One way you can determine if a function is even or odd without looking at the graph is to look at all the terms in the equation. If all exponents on all terms show all even or all odd numbers, then the function will be classified as even or odd respectively. However, if there's even one outlier, the function will be classified as neither. Now, before we talk about the functions themselves, let's go over the specific terms we use to describe the different components within a function. The most important terminology to know is the y-intercept. This is just where the function intercepts the y-axis. Or another way to think about it, the value of the output when x is equal to 0. This definition is the same for every type of function. The y-intercept here would still be the point where it crosses the y-axis. The y-intercept here would also still be the point where it crosses the y-axis. The y-intercept here would also be the point where it crosses the y... Oh wait, there is no y-intercept. Pop quiz, why is there no y-intercept here? If you said it's because there is a vertical asymptote, congratulations, here's a sticker. This is a rational function, which means x cannot be 0. Therefore, since the definition of the y-intercept is when the x is 0, there cannot be a y-intercept. Crazy how everything connects, huh? Another term to know is the zero of a function. This refers to where the function crosses the x-axis, or another way to think about it, when the value of the input gives a 0 as an output. I promise it sounds more confusing than it actually is. Pinky promise. For example, in this example, for the output y to equal to 0, the input x would have to be a 5 or a negative 5, which means the function would look like this, where you can see there are two places in which the function crosses the x-axis, at precisely 5 and negative 5. As if that's not confusing enough, we can also do something called transform a function, like transformers or something. This refers to when we either shift a function up, down, left, or right. To transform a function up or down, we do this by adding or subtracting a number to the entire function itself. We can transform a function like this when we give an input of 5 that gives an output of, let's say, 10. Then, when we add a number to the entire original function, keeping the input the exact same, the output will now be 17, with the addition of the new number, 7 in this case. Similarly, let's say we input an 8 to the original function. This would give an output of 16. Now, with the modified function, when we give an input of 8 into the function, the output is now 23. See the pattern? For the same input, the output is now shifted 7 more than the original output. In effect, the function shift would look like this. Shifting a function left or right is the exact same idea, just with a twist. Because math can never be simple or straightforward. Shifting a function horizontally involves adding or subtracting a number to the x value, or input value, except the twist is that the function will shift opposite to the sign that was added. So, unlike a vertical shift, if a number is added to the x value, the function will shift left or in the negative x direction. If the number is subtracted to the x value, the function will shift right or in the positive x direction. Horizontal is really just vertical with a twist. And now, finally, for the many, many different types of functions. Specifically, there are 9 function types that you're required to know in algebra. The most basic function of them all is a linear function. These are exactly what they sound like. Linear. Like a line. A linear line. Say that 10 times fast. The equation for a linear function is y equals mx plus b. In such an equation, the two very important components that will haunt you in your dreams forever as long as you take a math-related course are the slope and the y-intercept. The slope describes the predicted amount that the y, the output, would increase for every additional increment of the x, the input. So, for example, for every additional hour you work walking your neighbor's dog, you receive an additional $5 in payment. Or, for each additional win of the Philadelphia Eagles, the predicted number of fans increases by 10,000 people. Can you tell that I don't watch the Super Bowl? Or, for every additional example I give you to describe slope, the predicted probability that you will fall asleep increases by 20%. But, you get the idea. For the function to be truly linear, the increase in y must be constant for every constant increment of x, which we'll see that is not the case for any other type of function. And then there's the vertical intercept, which is just a number added to the x term. You should remember this from a minute ago. Quadratic functions are the u-shaped functions. Quadratic with a u. Anyway, quadratic functions always have a degree of 2, which is really what gives the quadratic function its u-shape. The sign of the leading coefficient. Pop quiz, what's a leading coefficient? The sign of the leading coefficient will determine if the function is a right side u or an upside down u. The direction of the u follows the sign of the leading coefficient. If the leading coefficient is positive, the shape of the graph will be right side up. If the leading coefficient is negative, the shape of the graph will be upside down. Very straightforward. I love quadratic functions because they're so straightforward, wonderful, amazing, fantastic. Wait, what's that? The equations we were looking at before were called standard form. This is called vertex form, and it looks like this. This isn't just some random math nonsense, even though it may feel like it. This is literally handing you the graph on a silver platter. Why? Because h, k is the vertex of the parabola, the lowest or the highest point, depending on which direction it opens. You might be thinking that this form tickles something in your memory, and you would be correct. Recall that shifting of a function left or right we were talking about before. Notice how h is subtracted from the x value, and k is added to the entire function. This makes sense because imagine if h was negative. In vertex form, a negative h would equate to the h being added to the x value. Negative paired with a negative is a positive and all that. And in horizontal shifting terms, adding a value to x means the function shifts left, which directly agrees with the rule that the vertex is h, k, because having a negative h value would mean that the vertex on the left side of the graph. The k value is much simpler to explain. Notice how k is added to the entire function, which indicates that the function is shifted up or down by k. This also agrees with the vertex form because if k is positive, then the vertex shifts up by k, and if k is negative, the vertex shifts down by k. The a value in vertex form will also be your best friend in picturing the quadratic graph. If a is positive, the graph will be opening up, and if it's negative, the graph will be opening down. It's like a mood ring, but for graphs. Also, we look at the magnitude of a. If the magnitude, or in other words, the absolute value of a, is less than 1, the graph will be wider. If the magnitude of a is more than 1, the graph will be narrower. Okay, now maybe we can move on from quadratics, until they come back in your nightmares. Now for radical functions, which is any function that involves a radical sign. This can mean square root, cubic root, and any other root under the metaphorical sign. The domain of any radical function that is even, like these, must be positive x values. This is because it is impossible to take an even root of a negative number. For an odd radical function, however, all positive and negative x values are fair game. Exceptions depending on how the function actually looks. For example, if there's a vertical asymptote anywhere. The most common radical function you will see are square root radical functions, which look like this. Square root functions are the inverse of quadratic functions, which means the graph looks like a quadratic function turned 90 degrees and cut in half to follow the vertical line test. If that's too complicated to understand, just know that the parent square root function looks like this, and you'll be set for life. Who am I kidding? Rational functions involve a polynomial divided by another polynomial. If you thought one function was enough to give you a headache, now you got two. Prepare to have an absolute monster migraine attack. In a rational function, the numerator and the denominator are both polynomials. Usually the drama comes from the denominator, because we're not allowed to divide by 0. And as we've learned, my dear pupil, what happens when we plug in an input value that gives a denominator of 0? A vertical asymptote! Finding where the vertical asymptote of a rational function is pretty straightforward. Just set the function in the denominator to 0 and solve for x. That will give you the x value where there is a vertical asymptote. However, as we've also learned, math is never simple or straightforward, so of course there are exceptions to this rule. Holes. Holes are exactly what they sound like. Holes. Holes occur if a factor appears in both the numerator and the denominator, and cancels out. The graph quite literally says, we were going to go there, but never mind. I'll go into more detail about holes in another video, but for now, just remember holes occur when there's a common factor in the numerator and the denominator. Here, something called a domain is also used to describe the function. The domain of a function is basically a set of all the possible input values. To find the domain of a function, start with all real numbers, then subtract whatever value makes the denominator equal 0. Those are excluded from the domain. Typically, we denote the domain of a function in interval notation, like this, where parentheses indicate the end value of the interval is not included, and brackets indicate the end value in the interval is included. Also, we have these U-shaped symbols and upside-down U symbols. For domain, we usually use the upside-down U symbol because that essentially means and. So our interval notation would read infinity to -5 and -5 to infinity, parentheses at -5 because x equals -5 is not included. There's an easy way to remember the and symbol. Notice how the upside-down U looks like an A without the line in the middle. A for and. Exponential functions may seem simple, but because math is never simple or straightforward, of course there are 4 core variants of exponential functions. These variants are made possible by the exponential function formula, which looks like this. The sign of the a value in front determines if the function is increasing or decreasing, and the b value determines if the function is growing or decaying. Where the x value is located really gives exponential function its name. Notice the variable is in the exponent, not the base. That's what makes it exponential. The 4 variants of exponential functions are increasing growth, increasing decay, and decreasing decay. Remember, growth always goes towards infinity, and decay always goes towards 0, but it never reaches 0 or infinity. The sign of infinity depends on if it's an increasing growth or a decreasing growth exponential function. In my opinion, logarithmic functions are the most complicated to understand. Technically, log functions are the inverse of exponential functions. The specifics of why this is a story of its own, and I'll cover it in a future video. For now, know the base form of a log function, and that there is always a vertical asymptote at x equals 0, and x can never be negative. Another function type that can never be negative are absolute value functions. The parent form of an absolute function looks like this, which can be modified to look the general form, which looks like this. If you don't see the similarity by now, I'll help you out.
The equations we were looking at before were called standard form. This is called vertex form, and it looks like this. Because h comma k is the vertex of the parabola, the lowest or the highest point, depending on which direction it opens.
Just like quadratic functions, absolute value functions also have a vertex at h comma k. And just like quadratic functions, the a value acts as an opening direction signal and a vertical stretcher. You're probably wondering why absolute value functions look like a V. If you're not, Merry Christmas, I'm going to explain anyway. The two vertical lines framing the x indicates that no matter what number you plug in, the output will always be a positive version of that number. So, a negative 5 would give a positive 5, and a 7 would still give a 7. Now, let's see what that does to our function. Notice how an absolute value function looks like two linear functions coming together. Aww. And, more importantly, that they mirror each other. That's because of this flipping of signs. When you plug in an x equals negative 5 and x equals 5, we get the same output of y equals 5. And the same for x equals negative 4 and x equals 4, and x equals negative 3 and x equals 3, and so on and so forth, which ends up giving us something that looks like this. I should also mention that absolute value functions can be split into two separate functions using piecewise form, which, speaking of, is our last but certainly not least type of function, piecewise functions. These functions are made up of multiple equations, each applying to a different part of the domain. Remember that migraine attack you had before? Yeah, well you might as well just replace your head this time, because you got multiple functions with different requirements for their usable x values. Let's look at the most basic example of a piecewise function, an absolute value function. These functions have two components, the decreasing linear function and the increasing linear function. We can write these two parts as separate equations. Then, since this equation applies to all negative x values, and this equation applies to all positive x values, we will assign that part of the domain to each respectively. And voila! We have ourselves a wonderful piecewise function. Piecewise functions come in all types of forms, and they do not have to be continuous. In fact, most aren't. You'll most likely be asked to solve for an output value when you plug a certain x value, rather than graph the entire function. To solve, look to the domain rules. Find which interval the x value lies within, then use the corresponding function to solve for the output. Plug in your x to that function and find the y. In the case that you're asked if the function is continuous, just check the endpoints of the domain intervals. If the shared endpoint, in this case 3, gives the same output in both functions, then the function is continuous at that point. If not, then the function is discontinuous. This would be much easier to spot in a graph. The open dots show that the end value is not included in that specific subfunction, and closed dots show that they are.